If this is your first time here, this isn't a standalone video. It's one chapter in a complete story, the entire history of evolution, from the first replicating molecules to you. Every organism we mention is your direct ancestor, not a cousin species, not something similar, your actual lineage, an unbroken chain connecting you to the origin of life. That's what makes this different from every other evolution content out there. Most of it is scattered fragments, dinosaurs here, early humans there, the Cambrian explosion somewhere else, all disconnected. But they're not disconnected. They're all chapters in the same story, your story, and you can't understand any link without seeing what came before it. Lungs don't make sense without swim bladders. Mammals don't make sense without reptiles. Each chapter builds on the last, and nothing appears out of nowhere. 4 billion years of your deep history told is one continuous thread. If that sounds interesting, Chapter 1 is in the top right corner. I'd recommend starting there. If you've been watching from the beginning, you already know what this is. Let's keep going. Vesicles now drift through warm surface waters, some empty, some carrying RNA or peptides trapped inside. Most do nothing, just passive bubbles that form, float, and eventually break apart. But a few contain something different, RNA that can catalyze reactions. These rare vesicles become the first chemical systems that might eventually be called alive. The transformation happens when a vesicle encloses RNA capable of building more RNA. Activated nucleotides, small enough to slip through the membrane, drift inside. The catalytic RNA grabs them and links them together. New chains accumulate because they're too large to escape. If one new chain folds into a catalytic shape, now there are 2 RNA molecules building more RNA. The vesicle becomes a factory. This creates the first meaningful difference between vesicles. Empty ones drift passively. RNA-filled ones grow because accumulated chains push outwards on the membrane. The membrane responds through simple physics. Stretched lipid bilayers have gaps where new fatty acids insert from surrounding water, expanding surface area. Eventually, the vesicle becomes mechanically unstable, too large, wrong geometry. A current deforms it into a dumbbell. The neck pinches, and 2 smaller vesicles form, each inheriting roughly half the parent's RNA. Jack Skozak's lab at Harvard demonstrated this exact process. They created protocells containing RNA, provided activated nucleotides, and watched the vesicles grow and divide mechanically. No genes controlling it, no proteins coordinating it, just physics and chemistry. Over hundreds of generations, RNA-containing vesicles outnumber empty ones because the former divide more often. Automatic filtering, the ones that work persist, and the ones that don't disappear. But there's a problem that nearly ends everything. Copying isn't accurate. Primitive ribozymes make roughly 1 error every 50 to 100 nucleotides. After 10 rounds of copying, most descendants are garbage. Wrong bases everywhere, broken chains, non-functional shapes. A ribozyme producing 9 useless copies and 1 functional one should be doomed. Errors accumulate faster than selection can fix them. This is called error catastrophe, and should make molecular evolution impossible. But here's why it doesn't destroy the system. Competition within finite space. A vesicle 1 micrometer across holds roughly 1 femtoliter of water. If that vesicle contains 1,000 RNA molecules competing for perhaps 10,000 activated nucleotides entering per hour, copying speed matters. An RNA sequence copying itself in 2 hours claims more resources than one taking 4 hours. After 10 generations, the faster copier produces 10,024 descendants, while the slower produces only 59. The faster sequence now controls 95% of the vesicle's RNA. But speed isn't enough. An RNA copying fast but making errors every 20 nucleotides produces mostly garbage. An RNA copying slowly but accurately, only 1 error per 200 nucleotides, maintains functional sequence better. The optimum isn't maximum speed, it's the right balance between speed and accuracy. Gerald Joyce's lab at Scripps evolved RNA molecules that improved their copying fidelity from 1 error per 50 bases to 1 error per 200 bases through selective pressures alone, proving selection can favor accuracy when accuracy demonstrates survival. Some RNA sequences discover something even more valuable. They catalyze reactions helping the vesicle itself. In 2013, Sheriff Manzi's lab in Italy showed certain ribozymes can catalyze fatty acid synthesis inside vesicles. When RNA produces fatty acids that insert into the membrane from inside, the membrane grows faster. That vesicle divides every 12 hours instead of 24, leaves twice as many descendants, and the RNA sequence spreads. The RNA that helps its container wins. Now the crucial transition begins. RNA starts directing peptide assembly. Some RNA sequences grip amino acids in specific pockets through chemical complementarity. A pocket shaped to fit lysine long, positively charged side chain holds lysine better than other amino acids. No code yet, just physical fit. If the RNA pocket positions two amino acids close together, they link, forming a dipeptide. Different RNA shapes produce different dipeptides. Here's what makes this revolutionary. RNA sequence determines pocket shape, which determines which amino acids fit, which determines what peptides get built, which determines what the peptide does chemically. The transition to true coded translation happens through adapter molecules emerging gradually. Some short RNA chains, 10 to 15 nucleotides long, fold into shapes with two distinct ends. One end binds a specific amino acid through a chemical affinity. The other has a sequence that base pairs with complementary sequences on other RNAs. These proto-transfer RNAs create a physical link between RNA sequence and amino acid identity. The critical insight is that proto-tRNAs aren't irreducibly complex. Each function existed separately before combining. RNA molecules that bind amino acids already existed. Many ribozymes used amino acids as cofactors. RNA molecules that recognize specific sequences through base pairing already existed. That's just how copying works. But a molecule doing both isn't a leap. It's just combining the two existing capabilities. The first proto-tRNAs were probably terrible at both jobs, binding amino acids weakly, recognizing sequences imprecisely, but even 10% specificity beats a random incorporation. Peptides made with this system would have certain amino acids appearing more often at certain positions than chance predicts. Any improvement in specificity, tighter amino acid binding, more accurate sequence recognition, gets selected because better correlation means more reliable production of useful peptides. Earth held perhaps 10 to the 22nd power protocells at any time during this period, each divided roughly daily. Over 100 million years, that's 10 to the 30th evolutionary experiments. The proto-tRNA innovation, however improbable for a single protocell in a single generation, only needed to happen once. With 10 to the 30th trials, even 1 in a trillion events become statistical certainties. Peptides transform protocell capabilities. Some peptides stabilize RNA, extending functional lifetimes from hours to days. Some catalyze reactions RNA handle poorly. Some interact with membranes controlling what passes through. Each function helps the vesicle, helps the RNA that produced the peptide, and spreads that RNA sequence through descendants. RNA dominates these early systems because it can store information like DNA and catalyze reactions like proteins. But RNA has crippling limitations. It breaks down in water within hours or days, and it's mediocre catalyst compared to proteins. The solution is division of labor, emerging gradually. Some ribozymes evolve the ability to chemically modify nucleotides before incorporating them. One crucial modification removes one oxygen atom from ribose sugar, creating deoxyribose. But why would this mutation be selected for before DNA's advantages are obvious? Well, because even mixed chains benefit immediately. An RNA chain with 10% deoxynucleotides lasts roughly 30% longer before breaking down. If that RNA is catalytic, longer lifetime means more work done, means more products made, means more benefits to the vesicle. The advantage is immediate, even for hybrid chains. Over time, protocells evolve ribozymes, producing deoxynucleotides more consistently. Eventually, chains made entirely from deoxynucleotides, DNA, serve as stable backup storage while RNA continues as working copy. This arrangement solves error accumulation. RNA copying RNA propagates errors forward, with each copy templating the next generation. But if DNA serves as a master template and fresh RNA copies are made from DNA each generation, errors in RNA copies don't compound. Only errors copying DNA matter in long term. DNA copying can be slower and more careful because it happens less frequently. Mutation rates drop from 1 per 100 nucleotides to 1 per 10,000 nucleotides. Information preservation becomes possible. By this point, protocells contain information stored in DNA, working copies in RNA, functional molecules as peptides, membranes that grow and divide, and primitive metabolism producing useful products from raw materials. They maintain themselves against entropy. They reproduce. They pass information to offspring. Success depends on how well their molecular contents cooperate. This is the edge of life. They still lack regulated metabolism, sophisticated membrane control, or complex genetic codes, but they have the core properties: self-maintenance, reproduction, information transfer, and improvement through selection. Everything afterwards is elaboration. The planet now holds systems that don't just exist, they persist, adapt, and evolve.